In this video, I want to talk about the Laurent expansion theorem. It's going to be very similar to the Taylor theorem that we talked about previously, but let's just set it up. So let's let capital R and capital R1, capital R2 be numbers, and I'm going to write this a little bit differently than the book does, but I think this should still be pretty clear. Capital R1 is greater than or equal to 0, R1 is less than R2, and then R2 can be anything else, including infinity. So when I write that R2 is less than or equal to infinity, what I mean is that we're allowing R2 to be infinity. That's part of the possibilities there. Likewise, we're allowing R1 to be 0. Okay, so let capital R1 and capital R2 be here in this range. Let's let Z0 be some value in the complex plane, and set, I'm just going to set A for annulus to be the set of complex numbers where Z minus Z0, the modulus is greater than R1 but less than R2. This might be slightly backwards from the way I wrote it before, but the idea is pretty simple. We just have an annulus. I'm going to call this A. R1 will be the inner radius, R2 is the outer radius. And then let's also let B be the set of complex numbers where, let's say, little r1 is less than or equal to the modulus of Z minus Z0, less than or equal to little r2, where little r1 and little r2 satisfy the following. So these are numbers in between r1 and r2. So big R1 is less than little r1 is less than little r2 is less than big R2. And the idea here is that we're going to take some annulus. Okay, so maybe Z0 is at the center here. So here's our capital R2, and then capital R1 is going to be some smaller value there. And then little r1 and little r2 are going to be some intermediate values, so some circles there in between. Okay, so maybe something like that. I want to move this over just so it looks a little bit better and it's centered. Okay, and then that's going to be our annulus there. So this would be a closed annulus between little r1 and little r2. Okay, you could probably guess where this is going to go. So A is the open annulus where the inner radius is capital R1 and capital R2. B is the closed annulus where the radii are little r1 and little r2. And then let F, so let's let F have a Laurent series A sub n, Z minus Z0 to the n, as n goes from 0 to infinity, plus as n goes from 1 to infinity, B sub n, Z minus Z0 to the negative n. So as usual. So that's our Laurent expansion. Okay, so then this F is absolutely convergent. So it's absolutely convergent on A and uniformly convergent. So, and uniformly convergent on B. Okay, and our values here, so A sub k is equal to 1 over 2 pi I times the integral over some circle. Let's just say over, yeah, that's fine, over some circle centered at Z0 of radius little r of f of w over w minus Z0 to the k plus 1 dw, and that's if k is greater than or equal to 0. And b sub k is going to have a very similar formula, 1 over 2 pi I times the integral of the circle of radius little r of f of w times w minus Z0 to the n minus 1. So that's if n, I don't know why I just mixed n and k, so let's call it k to the k minus 1. If k is, I need to be a little bit careful here, k is greater than or equal to 1. Okay, and so our a sub k's and our b sub k's satisfy the same formulas that we think of. One of the things that happens in Laurent series, and I should mention this, is that sometimes it's a convention to think of b sub k as a sub minus k. And then what you can do is you can think of the Laurent series as the sum from negative infinity to infinity of the usual thing of a sub k, z minus z naught to the k. Okay, and then your negative powers correspond to the negative indices for your exponents. So if you have a minus 2, that's going to be to the power minus 2. Okay, so here you have kind of a two-tailed series. So it goes to negative infinity and infinity. And if you do it like this, then you can kind of just get away with writing a single formula for a sub k for all k. Okay, and so anyways, so that's the idea. Here I forgot to mention, here R is in between R1 and R2, little r1 and R2. So it's just some circle centered at z naught of radius r. Okay, so just centered in there somewhere. And really any positively oriented piecewise smooth curve that contains z naught in the inside of it will work. Really, there's nothing special about R. So all the usual stuff applies. Okay, so all the usual deformation and all that. So anyway, so just take a standard circle since that's good enough. Okay, but this is a Laurent expansion theorem. So if you have a Laurent series, the idea here is that it's absolutely convergent on the open annulus. It's uniformly convergent on an enclosed annulus inside that open annulus. The coefficients have formulas that are just like before. And there's one more thing, one more punchline. This Laurent expansion is unique. Okay, so this Laurent expansion is unique. And I should say it's unique on A. Okay, and that's the idea. So these are basically exactly like Taylor series, and everything works out more or less the same there. I am not going to go through and formally prove this, because to prove this for the non-negative terms, it's just Taylor's theorem. To prove this for the negative terms, you have to massage it a little bit, but then essentially it amounts to Taylor's theorem again. So you do all the usual stuff, all the stuff that we did in previous videos. So I think just in terms of bang for a buck, I'm going to skip the proof of this. But again, the proof is in the book. I would encourage you to read over it at least once to see some of the details.